All right, let's just dive right into this explainer. You know, as a technology historian, I get the absolute privilege of looking back at humanity's epic, centuries-long quest to solve complex problems faster and more efficiently. We are basically going to trace this incredible relay race of innovation, one that starts quite literally with counting on our fingers and leads us all the way to modern artificial intelligence. Today, we're going to unpack exactly how we got here, breaking down those massive and honestly sometimes accidental leaps in technology that completely transform the human experience.
Here's our roadmap for today. We'll be covering 1. Early counting and mechanical minds. 2. The dawn of electronic computing. 3. The silicon microchip revolution. 4. Personal computers and the internet. 5. Mobile devices and the cloud. And finally, 6. Artificial intelligence and tomorrow.
Starting off with Section 1, Early Counting and Mechanical Minds.
To really wrap our heads around computing, we have to go all the way back to the beginning and ask a pretty basic question. Why did early humans even need counting systems in the first place? Picture the ancient world, right around 3000 BC. As early civilizations started building cities and setting up trade routes, they ran into a very real data problem. They desperately needed reliable ways to track agricultural cycles, store inventory, and manage commerce. I mean, when you're trying to manage an entire kingdom's green supply, you can only count so high on your fingers, right? This urgent human need to track and calculate gave birth to the abacus, which is really one of our very earliest computing tools. But as human ambition, global commerce, and science expanded over the next few millennia, well, the math got significantly harder. Fast forward to 1642 CE, and we see the invention of mechanical calculators like the Pascaline. These were these intricate physical machines made of brass cogs and gears. They were specifically designed to take the tedious, heavy lifting of addition and subtraction off the human brain, but they still required physical effort and moving parts to actually work.
And there's this brilliant quote from Ada Lovelace that perfectly illustrates the human vision behind all those early gears. Back in the 1830s, a mathematician named Charles Babbage designed this massive, incredibly complex mechanical computer called the Analytical engine. Picture this. It was meant to be the size of a house and powered by a literal steam engine. But it was his collaborator, Ada Lovelace, who truly saw its world-changing potential. She realized this machine wouldn't just sit there and crunch numbers for accountants. Using the metaphor of a mechanical loom, she understood that a machine could process any kind of symbolic information, as long as it was given the right instructions. Because of this profound foresight, recognizing that numbers could represent things way beyond just quantities, Ada Lovelace is widely recognized today as the world's very first computer programmer.
So how do you actually talk to a giant mechanical beast made of brass, steel, and steam? The ingenious answer was punch cards. You'd punch a highly specific pattern of holes into a stiff piece of paper to represent your data or your command. Then you feed that card into a mechanical reader. The presence or the absence of a hole physically allows a pin to pass through, which triggers the machine to execute a specific instruction. This was a massive historical milestone for sure. It was the very first physical form of software. But just imagine the tedious reality of this. Programmers had to manually punch thousands of holes and carry around massive, heavy stacks of cardboard. Literally, if you tripped and dropped your stack of punch cards on the floor, your entire program was completely ruined.
Moving right along to Section 2, the dawn of electronic computing.
So Charles Babbage definitely had the vision, but physical, mechanical parts simply couldn't move fast enough. The manufacturing tolerances back then just couldn't build gears precise enough for his grand designs. Before we could build the electronic hardware of the future, we actually needed a mathematical blueprint first. Enter Alan Turing in 1936 and his groundbreaking concept, the universal Turing machine. Now, this wasn't some physical object you could touch. It was a mathematical model of an abstract machine. Turing proved theoretically that a single, versatile machine could be reprogrammed to perform absolutely any conceivable algorithmic task. You didn't need to build a brand new physical machine every single time you encountered a new math problem. You just needed to change the recorded instructions. This concept, it's the foundational DNA of every single computer, smartphone, and video game console you use today.
When we compare those old, clunky mechanical calculators to the physical reality of the ENIAC, the leap in capability is absolutely staggering. Those old calculators were severely limited by spinning physical gears. They were super loud, incredibly slow, and honestly, they broke down constantly. But the ENIAC, completed in 1945 for the military to calculate artillery firing tables, it completely ditched the moving gears for electronic vacuum tubes. By using the lightning-fast flow of electrons rather than spinning brass wheels, it was exponentially faster. But man, it was a beast. It weighed nearly 30 tons, took up an entire 50-foot room, and used 18,000 glowing, incredibly hot vacuum tubes. In fact, it drew so much power that rumors claimed it actually dimmed the lights of Philadelphia when it was turned on. But despite its massive footprint, it was a reprogrammable electronic brain. Computing had officially left the mechanical age.
Let's look at Section 3, the Silicon Microchip Revolution.
Okay, so we finally had electronic speed, but we immediately slammed into a new massive problem: size and heat. Those vacuum tubes were terribly bulky, they consumed massive amounts of electricity, and because they ran so hot, they burned out constantly. Technicians had to frantically run around replacing them just to keep a program running. The hardware desperately needed to shrink, and this necessity sparked 3 crucial milestones. In 1947, engineers at Bell Labs invented the transistor. This was a tiny, solid-state device that completely replaced the fragile vacuum tube. It acted as a much faster, cooler electronic switch with 0 moving parts. Then, in 1958, engineers figured out how to put multiple transistors onto a single flat piece of material, creating the integrated circuit. Finally, in 1971, the ultimate miniaturization happened with the Intel 4004, the microprocessor. They miraculously managed to put an entire central processing unit, the core calculating brain of the computer, onto one single tiny silicon chip.
The absolute most crucial takeaway of this era is scale. The sheer absurdity of this engineering feat really cannot be overstated. That early 1971 microprocessor held a little over 2,000 transistors. Today, a single modern microchip inside the phone currently sitting in your pocket contains literally billions of microscopic transistors. We are now manufacturing components at the atomic scale. The room-sized 30-ton ENIAC supercomputer that required a whole team of engineers to operate is now millions of times less powerful than a standard smartwatch. This relentless miniaturization is exactly what drove computing power into the stratosphere while simultaneously driving costs and physical size into the floor.
Bringing us to Section 4, Personal Computers and the Internet.
Shrinking all this hardware finally allowed computers to leave those massive, well-funded university and government laboratories. We entered the era of the early microcomputer. Built by hobbyists tinkering in garages and eventually by massive corporations, these were personal, desktop machines built for everyday individuals to have in their homes and offices. But initially, they were entirely isolated. Your computer couldn't talk to my computer. We literally had to physically hand each other floppy disks just to share data. But that all changed with the Internet era. By creating a globally connected network using standardized protocols, we linked all of those isolated desktop machines together. The computer fundamentally transformed almost overnight. It went from being a standalone, glorified calculator and word processor sitting on a desk to a magical portal into a vast worldwide web of human knowledge, commerce, and communication.
Which leads directly into Section 5, Mobile Devices and the Cloud.
Once we were all connected, human nature just kind of took over. We wanted that powerful connection everywhere we went, not just when we were sitting at a desk. This sparked the massive smartphone revolution of the late 2000s, which was built on a few key pillars. We combined constant wireless internet connectivity with pocket-sized touch interfaces. Suddenly, the power of a desktop computer was right in the palm of your hand while you were just walking down the street. But there's a pretty clever hidden engineering trick going on here: offloading heavy data processing to remote servers. Your smartphone is incredibly powerful, sure, but to do the truly heavy lifting, like instant real-time language translation or rendering global mapping data with live traffic updates, it doesn't rely solely on its own internal microchips. It packages that data up and sends it outward.
So, where exactly does that data go? Well, it goes to the cloud. Cloud computing is simply the delivery of vast computing services over the internet. And to be totally clear, it's not actually floating up in the sky. When you stream a 4K movie or ask your phone's voice assistant a complex question, you are pulling that data from your phone's tiny local hard drive. You are instantly tapping into massive, highly secure data centers located perhaps hundreds of miles away in places like Virginia or Oregon. These centers are filled with thousands of synchronized computers just humming together. The cloud is basically the invisible backbone that makes your small mobile devices feel infinitely powerful.
And that brings us to Section 6, Artificial Intelligence and Tomorrow.
decades of shrinking microprocessors down to the atomic level, combined with the massive, sprawling data storage of cloud computing, finally gave us the raw computational power needed to achieve a dream we've had since the dawn of the electronic age: artificial intelligence. AI refers to systems or machines that mimic human intelligence to perform tasks, but the most important phrase here is capable of learning and iteratively improving themselves. Think about it. We are no longer just feeding rigid punch cards into a brass machine to execute a single static math problem. We are building incredibly complex neural networks that can recognize medical patterns in X-rays, generate breathtaking art, understand conversational speech, and literally learn from their own mistakes. It is the breathtaking culmination of everything from the ancient Abacus right up to the silicon microchip.
I want to leave you with a final thought to chew on. From tracking early trade inventory with an abacus, to Alan Turing's brilliant theories, to billion transistor chips and machines that can actually think, what in the world will be the next great leap? Will quantum computing completely rewrite the physical rules of silicon that we've relied on for decades? Will biological computers, powered by synthetic DNA, be next? As a historian, I can tell you this for sure. Every single time we think we've reached the absolute physical limit of computing, some brilliant mind comes along and shatters it entirely. The relay race is far from over. Thanks for joining me on this explainer. Keep wondering, keep learning, and I'll catch you on the next one.